Hey guys, welcome back to my channel. My name is surface-Ekman and I've got some pretty exciting stuff for you today. It's been a while, I know, I'm so sorry. I totally have been occupied with some research. You all know that I'm a big fan of Professor Nansen. Go subscribe to his channel, Professor Friedhoff, if you're not already subscribed, because I saw something in one of his last videos and it was just so fascinating. I will show you guys just in a minute. So, when I saw this video, I just wanted to do some low-key calculations, but it turned into a couple of weeks of exhausting research. But now, I'm really excited to share some results with you. But first, let's check out this video of Professor Nansen on his recent influencer cruise to the Arctic.
This is Nansen. I'm on a front cruise in the Arctic, and I just saw this very interesting thing. Drift, produced by a given wind, does not follow the wind's direction, but deviates 20 to 40 degrees to the right. And I'd even think that the water layer, deep below the surface, must have a somewhat greater deviation than the surface itself. And I think that at some depth, the currents would even run in the opposite direction to the surface current.
So go subscribe to Nansen's channel if you haven't already. And now let's get started on the derivation. How amazing would it be to describe this observed current with our beloved mathematics? Well, it is possible. It is now 1905 and I just published a paper about it. I'm gonna show you guys the steps of my original paper. Here you can see it. It is just amazing. Go get your copy and read it. We start with the equation of motion of the water. What can I tell you guys about it? Well, we take z as the vertical, which is positive downwards. We also suppose that the sea surface is impelled by a steady and uniform wind equal in strength and in direction over the whole region. And this wind has lasted so long that a practically stationary state of motion has become established. Well, that's a whole mouthful. What does it mean? It simply means that these terms over here are all equal to 0. Then we have these two terms, which are over here. These are the horizontal components of the deflective force due to the Earth's rotation, where omega is the angular velocity of the Earth and phi is the latitude. We take no other force but gravity into account, so the last two equations over here are unnecessary, and only these two equations are left. We already said that the motion is stationary, so the time derivatives vanish. And if we write A as this expression, and we can rewrite the equations into this form. Well, the general solution obviously looks like this, where C1 and C2, both capital and small letters, are all arbitrary constants. Okay, now we need boundary conditions. As a first boundary condition, we assume that the ocean is infinitely deep, so that the velocity is 0 for z infinite. Then we can see that C1 is 0. Before we continue, I would first like to talk to you about the sponsor of today's video, Frederick's fantastic fur coats. I use these fur coats all the time when I go on expeditions to the Arctic. They are made of low cruelty, 100% organic baby seal fur. Get your fur coat now with 10% discount with the code Ekman1905. Now, let's continue the derivation. Now, as a second boundary condition, we assume that the tangential pressure of the wind on the sea surface is called T, and it is directed along the positive axis of y. Now, if we differentiate u and v with respect to z, we get, with using this product rule and a trigonometric identity, these two expressions. Now we only have to fill them in with some constants, and we define v0 to be the absolute velocity of the water at the surface, and after some rearranging we get these beautiful expressions. Now one last thing before we wrap this up. is to define the depth of the wind current. We will just say that this is the depth down to that level where the velocity of the water is directly opposite to the velocity at the surface. This depth can then be defined by this expression. Now I also made a sketch of my findings. You can see it over here. You see the wind forcing T and the velocity vectors plotted on the xy plane. And you can see that I successfully, mathematically, described the phenomenon that Professor Nansen described. We can see that the surface velocity is beautifully at 45 degrees to the right of the wind velocity. And we can also see over here the velocity directly opposite to the surface velocity, which would then be the level D. Now that's it. But I'm not done yet, because as I do every week, I like to answer some questions of my fans. And this time I've got a very interesting message from Sarah. She says she's a student from the future, how exciting, and she has to do an assignment on a spiral, which is apparently named after me. She read my paper, and she wants to show me something. Now I don't know what these plots are, but you don't often get the chance to talk with a fan of the future. So, let's get Sarah into the video. Hey Sarah.
Hi, Vagen. Oh my god, it is so nice to meet you. I thought to reach out to you because it would be interesting for you to learn how we use your equations in the future. I, of course, read your paper that you published in 1905 that I think was super interesting. Unfortunately, some of the variable names and ways of formulating the equations aren't really up to the 21st century standards, so I'll quickly go through some changes I made before showing you the plots.
First, if we look at this expression for the depth of the wind current, we can easily see that we can express A as A is pi over d. Furthermore, we can express this part as the Coriolis frequency divided by 2. Then we can use the kinematic viscosity, which is the dynamic viscosity over the density, which we also have a value for. So with these new parameters, we can rewrite d like this. And now a few more changes. We let z decrease with depth now instead of increase. We express the angles in radians instead of degrees. And lastly, we rename the surface current V0 to US and give it a generic value of 1 meter per second. And then we rewrite the equations so we get this. One last thing I would like to add is that sometimes a different boundary condition is chosen. Vagen, in your derivation you use that the wind forcing is in the direction of the y-axis, but often this forcing is taken in the direction of the x-axis. But this of course doesn't really matter. I'll stick here to the original equations so you don't get confused. So, now that we have updated the equations to modern times, let's take a look at the plots. In this first plot, we have the depth on the y-axis and the velocity on the x-axis. We can see that u and v, the x and y components of the Ekman velocity, change direction with depth. If we look at the total amplitude of the velocities in green, we can see that it decays exponentially with depth, just as you would expect from this part of the equations. Furthermore, we see that indeed at z is 0, the velocity equals the velocity of the surface layer, which we defined as 1 meter per second. Now, can we derive the depth of the wind current from this plot? We know that at the surface u and v have the same size, so we want to know where they are the same size again, but are pointing in the opposite direction. Well, that is at this point. And if we calculate it, we see that this is indeed where the depth is d. In this second plot, I remade your first figure. We show the velocities in the zonal direction compared to the meridional direction. The first dot is the surface current, and you can really nicely see the inward spiral with the increase in depth, just as we would expect from the sine or cosine part of the equations. But now let's add a cool feature. I colored the dots according to their depth. And now let's figure out how we can see our depth of the wind current in this figure. Here it's very easy to see where the current is in the opposite direction as the surface current. The surface and the opposite vectors are indicated in red. We see that the velocity in the opposite direction corresponds to this bluish color, which of course again agrees with our calculation. And now I want to show you something really cool. I combined the previous two plots in a three-dimensional plot. I present to you the Ekman spiral in its complete form.
That is just amazing. How did you do that?
That are just some future technologies, but I'm not even finished. You have told me about Professor Nansen and his observations of this spiral at the surface, but do you know that the same phenomenon can be observed at the bottom of the ocean?
Whoa, really? How does that work?
So, in the 21st century, we call this phenomenon the bottom Ekman spiral. It can be derived in the same way as the surface-Ekman spiral, but instead of a wind forcing, we assume that the ocean interior has a geostrophic velocity, and the spiral then occurs when we have a no-slip boundary condition at the bottom. Furthermore, we say that z is 0 at the bottom. Maybe this is something you can derive in the next video, Vagen? Anyways, the equations look like this, and for the plots I use the same values for f and k to calculate d as before. We take 0.1 meter per second for the geostrophic flow in the x direction and assume that there is no geostrophic flow in the y direction, which simplifies the equations. Now, let's get straight to the plot. When we look at this plot, we immediately see something very surprising. The velocity in the direction of the geostrophic flow increases with depth in the upper part of the Ekman layer. That's cool, isn't it? Now let's look at d in this plot. It doesn't have the same clear meaning here as it has for the surface spiral, so we'll just say that the depth of the bottom Ekman layer is the distance over which it approaches the interior velocity. But one thing that we can see here is that when z equals d, the velocity v is 0. One last thing we can observe in this figure is that when we get near the bottom, that there is a flow in the y direction, so that v becomes non-zero. Very near the bottom, u and v are equal, so we would expect that the flow here would be 45 degrees to the left of the interior velocity, just like we also saw in the surface spiral. Let's look at it from above and see if we can see that 45-degree angle. We do indeed see what we expected. The velocity vectors near the bottom make a 45-degree angle with the interior current. And we also see what we saw previously, that the current higher up in the spiral has a velocity u that is larger than the velocity in the interior. Let's look at it one last time from all sides. What a beautiful phenomenon!
Thank you, Sarah. That was great. I am totally blown away.
It was a pleasure.
So that was Sarah. If you liked this video, don't forget to give it a thumbs up, hit the subscribe button, and I see you guys next week. Bye.